Right now, every atom in your body is spinning. The planet beneath your feet completes one rotation every 24 hours while orbiting a star that spins once every 27 days. That star circles the galactic center at 500,000 miles per hour, completing one rotation every 200 million years. Your galaxy itself rotates like a cosmic pinwheel, containing 400 billion stars all spinning in coordinated motion. But here is what should terrify you. Physics says this is impossible. The second law of thermodynamics guarantees that organized motion decays into chaos. Friction destroys rotation. Collisions randomize direction. Energy dissipates as heat. After 13.8 billion years, the universe should have ground to a halt. Every spinning structure should have stopped. Yet tonight, 2 trillion galaxies continue rotating in patterns established before the first atoms formed. Scientists discovered why rotation refuses to die, and the answer reveals that the cosmos carries an immortal memory of its quantum birth. If you want to understand the unkillable force that keeps reality spinning, hit that like button and subscribe. Prepare yourselves. We begin. Look at a hurricane from space. The spiral arms stretch hundreds of miles across ocean surfaces while wind speeds exceed 100 miles per hour. This rotating storm system contains more kinetic energy than 100 nuclear weapons. Yet within days, friction with the ocean surface and atmosphere will drain that energy away. The organized rotation collapses into random air currents. The hurricane dies. This same principle applies throughout nature. A spinning top slows and falls. A rotating wheel eventually stops. Even the most perfectly balanced mechanical systems lose energy to friction and air resistance. The universe operates according to the second law of thermodynamics, which states that entropy always increases. Organized motion transforms into heat. Structure decays into randomness. This law has no known exceptions. Rotation represents one of the most organized forms of motion possible. Every particle in a rotating system moves in coordinated circular paths around a common center. This coordination requires precise conditions. Change the velocity of just one component and the entire system becomes unbalanced. Add friction and the rotation slows. Remove energy and the spinning stops. Scientists can calculate exactly how long any rotating system should survive before entropy destroys it. A hurricane lasts days. A mechanical flywheel might spin for years in near-vacuum conditions. But eventually every rotating structure must surrender to thermodynamic law. The organized motion must decay. Therefore, the universe presents a paradox that violates basic physics. Galaxies have been rotating for over 10 billion years. Stars spin for billions of years without slowing. Planets maintain rotation across geological time. Even subatomic particles possess intrinsic angular momentum that never decreases. The cosmos teems with rotating structures that should have stopped spinning billions of years ago. The Milky Way completes one full rotation every 200 million years. Dinosaurs walked on Earth during the last galactic rotation, yet our galaxy shows no signs of slowing down. The spiral arms maintain their structure. Stars continue orbiting the galactic center at precisely calculated velocities. 400 billion stellar furnaces move in coordinated rotation, despite countless gravitational interactions that should have randomized their motions long ago. Confirmed observations reveal that distant galaxies observed as they existed 10 billion years ago rotated at speeds comparable to nearby modern galaxies. Cosmic rotation has not slowed detectably across half the universe's lifetime. This stability defies the entropy that destroys every other organized system. Even more disturbing, rotation appears at every scale of cosmic organization. Atoms contain electrons that possess intrinsic spin. Molecules rotate. Planets spin. Stars rotate. Galaxy clusters show coherent rotation across distances spanning hundreds of millions of light years. The cosmic web itself exhibits rotational patterns at the largest observable scales. This universal rotation cannot be coincidental. Some fundamental property of reality must preserve spinning motion across cosmic time. The question that haunted physicists for decades was identifying what physical mechanism could protect rotation from entropy's relentless destruction. Every other form of organized motion decays. Why does rotation survive? The answer would require discovering a quantity so fundamental to physics that the universe itself cannot destroy it. But before scientists identified this immortal property, they first needed to understand exactly what rotation means at the quantum level, where the rules of classical physics break down and reality becomes strange. In 1873, a physicist named James Clerk Maxwell identified a quantity that behaves unlike anything else in nature. He called it angular momentum. This property obeys one of the most rigid conservation laws in physics. Angular momentum can be transferred between objects. It can be redistributed across space, but it cannot be created from nothing, and it cannot be destroyed. The total angular momentum in any closed system remains absolutely constant forever. This conservation law operates with mathematical precision that permits no exceptions. When an ice skater pulls their arms inward during a spin, they rotate faster. Their body conserves angular momentum by increasing rotation rate as mass moves closer to the spin axis. The skater creates no new rotation. They simply concentrate existing angular momentum into a smaller radius, forcing faster spinning to maintain the conserved quantity. The same principle governs every rotating object in the universe. A collapsing gas cloud that takes 1 million years to complete a single rotation will spin much faster after gravitational forces compress it. As the cloud shrinks, conservation of angular momentum demands increased rotation rate. By the time that cloud becomes a star, it might complete one rotation every 30 days. The star spins thousands of times faster than the original cloud despite no external force adding rotation. This explains why rotation survives across cosmic time. Unlike linear motion that friction can stop by converting kinetic energy into heat, angular momentum has nowhere to go. Energy can dissipate. Momentum can be absorbed by external objects. But angular momentum in an isolated system remains locked at its initial value regardless of what internal processes occur. Confirmed experiments demonstrate this conservation with disturbing precision. Scientists suspended a spinning gyroscope in near-perfect vacuum and measured its rotation rate over months. The device showed no measurable decrease in angular momentum despite unavoidable quantum effects and microscopic friction. The spinning continued essentially unchanged, limited only by instrumental sensitivity. This immortality makes angular momentum unique among physical quantities. Charge is conserved, energy is conserved, but both can be hidden or transformed in ways that make them locally unavailable. Angular momentum cannot hide. It must manifest as observable rotation somewhere within the system. Transfer it from one object to another, and both objects will demonstrate the exchange through changed rotation rates. The mathematics of angular momentum reveals why this quantity resists destruction. Angular momentum equals mass times velocity, times distance from the rotation axis. This three-way relationship means that changing any one parameter forces compensating changes in the others. Slow the rotation, and the mass must move outward. Bring mass inward, and rotation must accelerate. The universe will not permit any change that violates this mathematical balance. But this raises a more disturbing question than it answers. If angular momentum cannot be created, where did all the rotation in the universe originate? Every spinning galaxy, every rotating star, every planet with day-night cycles possesses angular momentum that must have come from somewhere. The conservation law guarantees that this rotation was not created after the Big Bang. It must have existed from the beginning. Scientists mapping the cosmic microwave background searched for evidence of universal rotation. If the entire universe spins, that rotation would appear as specific patterns in the ancient radiation left over from when atoms first formed. Advanced satellites measured temperature variations across the entire sky, with precision reaching millionths of a degree. The results showed no signs of universal rotation. Space itself does not spin. The cosmos as a whole possesses zero net angular momentum. This creates an impossible situation. The universe contains countless rotating structures, yet the total rotation adds up to zero. For every galaxy spinning clockwise, another galaxy somewhere spins counterclockwise. The angular momentum vectors cancel out when summed across cosmic scales. Reality somehow produced infinite amounts of rotation, while maintaining zero total angular momentum. The resolution of this paradox requires understanding that angular momentum is a vector quantity, possessing both magnitude and direction. The universe can create rotation in any direction without violating conservation laws, as long as it creates equal rotation in the opposite direction. But this still does not explain the mechanism that generated rotation from an initially non-rotating state. The early universe existed as a nearly uniform soup of energy and matter. Tiny quantum fluctuations created microscopic density variations, but these variations showed no preferred direction of motion. How does a universe with no rotation produce galaxies that spin at 500,000 miles per hour? The answer lies in the smallest scales of reality, where quantum uncertainty makes the impossible merely improbable. The cosmic microwave background radiation provides a snapshot of the universe when it was only 380,000 years old. Advanced satellites have mapped this ancient light across the entire sky with extraordinary precision. Scientists analysed the data searching for any sign that the early universe possessed rotation. They found nothing. The temperature variations in the cosmic microwave background show patterns consistent with a universe that expanded uniformly in all directions. No spiral structure appears, no evidence of cosmic vortices emerges from the data. The polarization patterns of the ancient light reveal no hint of universal spin. By every measurement astronomers can perform, the universe as a whole has never rotated. This presents a staggering mystery. Today, rotation dominates cosmic structure at every observable scale. Yet the universe began with zero net angular momentum. The Big Bang created space, time, matter, and energy. But it created no rotation. The spinning structures we observe throughout the cosmos must have emerged from initial conditions that contained no spin whatsoever. Think about what this means. Every galaxy rotating through space, every star spinning on its axis, every planet with day and night cycles inherited their angular momentum from a universe that started with none. 2 trillion galaxies spin in coordinated patterns across cosmic space. Yet if you could somehow add up all their angular momenta as vector quantities accounting for direction, this sum would equal exactly 0. For every galaxy spinning in one direction, another galaxy somewhere in the universe spins in the opposite direction, with precisely matching angular momentum. The cosmos maintains perfect balance. This balance is not approximate or statistical. Conservation laws demand mathematical exactness. The total angular momentum of the universe must equal exactly 0, because it started at 0, and conservation laws prohibit any change to the total. But this raises the fundamental question that plagued cosmologists for decades. How does a universe with zero rotation create individual structures that spin? The conservation law appears to forbid the emergence of any rotation at all. If the universe begins with no angular momentum, it should remain forever without rotation. Yet reality directly contradicts this expectation. Scientists initially proposed that random processes during galaxy formation created rotation. Perhaps chaotic motions in early gas clouds produced net spin through statistical fluctuations. Computer simulations tested this hypothesis by modelling the collapse of gas clouds using only random particle velocities. The results showed that random motion cannot produce coherent rotation. Chaos creates more chaos. It does not spontaneously organise into coordinated spinning structures. Other theories suggested that gravitational interactions between forming galaxies transferred angular momentum between structures. One galaxy gains clockwise rotation, while its neighbour acquires counterclockwise spin. This mechanism can redistribute angular momentum, but cannot explain where the original rotation originated. The theory simply pushes the mystery back one step without solving the fundamental problem. The breakthrough came from understanding quantum mechanics at cosmic scales. During the first moments after the Big Bang, the entire observable universe was smaller than a proton. At these microscopic scales, quantum uncertainty dominates physical processes. The Heisenberg uncertainty principle states that you cannot simultaneously know both the position and momentum of any particle with perfect precision. This quantum fuzziness applies to angular momentum just as it applies to linear momentum. In the quantum realm, particles do not possess definite values for physical properties until those properties are measured. Before measurement, particles exist in superposition states containing all possible values simultaneously. This quantum uncertainty meant that the early universe did not have zero angular momentum in every microscopic region. Instead, each tiny volume of space contained quantum fluctuations in angular momentum that varied randomly in magnitude and direction. These quantum variations averaged to 0 when summed across the entire universe, satisfying conservation laws. But locally, in regions smaller than the Planck length, angular momentum fluctuated wildly due to quantum uncertainty. Some microscopic volumes possessed slight clockwise rotation. Others had counterclockwise spin. The fluctuations remain tiny, carrying angular momentum values that quantum mechanics barely permits. Confirmed calculations show that quantum uncertainty allows angular momentum fluctuations of approximately 10 to the negative 68 kilogram meters squared per second at the Planck scale. This represents an almost incomprehensibly small amount of rotation. A region of space the size of a proton containing this much angular momentum would complete one rotation in a time longer than the current age of the universe, multiplied by 10 to the 50th power. These microscopic quantum fluctuations should have remained forever insignificant. The tiny random variations in angular momentum should never have grown large enough to affect cosmic structure. But the universe had one more surprise in store. During the first tiny fraction of a second after the Big Bang, space itself underwent a transformation so violent that it amplified quantum whispers into cosmic roars. Cosmic inflation occurred when the universe was less than 1/trillionth of a trillionth of a trillionth of a second old. During this incomprehensibly brief period, space expanded by a factor exceeding 10 to the 26th power. A region smaller than a proton grew larger than the observable universe today. This exponential expansion happened faster than light could cross the distance of an atomic nucleus. The inflationary expansion stretched everything. Distance between points in space increased by colossal factors. Energy density patterns that existed at quantum scales were amplified to galactic proportions. And critically, the tiny quantum fluctuations in angular momentum were magnified along with everything else. Microscopic random variations in spin became macroscopic differences in rotation across cosmic space. Imagine drawing a dot on a deflated balloon with a fine-tipped pen. The dot measures 1 millimeter across. Now inflate that balloon until it reaches the size of Earth. That tiny dot expands to cover an area measuring thousands of miles. The pattern you drew at small scale now dominates the balloon's surface at planetary scale. Cosmic inflation performed this same transformation on quantum fluctuations. The quantum uncertainty that created angular momentum variations measuring occupied regions smaller than the Planck length. Inflation stretched these regions to sizes measuring millions of light-years across. The angular momentum contained within each expanded region remained constant, because conservation laws permit no other option. But the physical size of the rotating region grew by factors approaching infinity. This created a universe filled with patches of space that possessed slight rotational bias. Some regions contained microscopic excess of clockwise angular momentum. Others had counterclockwise preference. These biases remained tiny compared to the total mass energy in each region. But they were no longer quantum-scale fluctuations. Inflation had promoted them to macroscopic differences that could affect the evolution of cosmic structure. Confirmed observations of the cosmic microwave background reveal the fingerprints of these inflated quantum fluctuations. The temperature variations across the ancient sky map directly onto the density fluctuations that inflation created. Regions that were slightly denser in the early universe appear as warm spots in the microwave background. Regions with lower density show up as cool spots. The pattern matches theoretical predictions for inflated quantum noise with extraordinary precision. But the cosmic microwave background also contains subtler patterns that reveal angular momentum structure. The polarization of the ancient light shows swirling patterns that indicate rotational motion in the early universe. These vorticity patterns remain small and difficult to detect. But advanced analysis techniques have confirmed their presence. The early universe contained rotation at the moment when atoms first formed, and that rotation came from quantum fluctuations amplified by inflation. Scientists calculated the amount of angular momentum that inflation would generate from quantum uncertainty. The numbers match observed galaxy rotation rates with remarkable accuracy. A typical galaxy spanning 100,000 light-years contains angular momentum measuring approximately 10 to the 68th kilogram meters squared per second. This value is exactly 10 to the 136th power, larger than the quantum fluctuations that seeded it. The ratio between galaxy-scale angular momentum and its quantum origin equals precisely the expansion factor that inflation produced. The universe stretched space by a factor of 10 to the 26th. Angular momentum scales with the square of distance, producing amplification of 10 to the 52nd power in the angular momentum per unit volume. Multiply this by the increased volume of expanded space, and you recover the observed galactic rotation from inflated quantum seeds. This mechanism explains how a universe starting with zero total angular momentum produced countless spinning structures. The quantum fluctuations contained both positive and negative angular momentum in equal amounts. inflation stretched these fluctuations while preserving the zero-sum balance. Every region that gained clockwise rotation was balanced by another region with equal counterclockwise spin. Conservation laws remained satisfied while the universe filled with rotation, but inflation only created the potential for cosmic spin. The angular momentum existed as slight biases in velocity distributions across vast regions of space. Converting these subtle rotational patterns into the concentrated spin of galaxies and stars required another fundamental force. Gravity would take the diffuse rotation that inflation created and compress it into the violent spinning structures we observe throughout the cosmos. The gentle quantum whispers were about to become screaming cosmic hurricanes. Gravity does not create angular momentum, but it concentrates rotation with ruthless efficiency. When a cloud of gas begins collapsing under its own gravitational attraction, any rotation present in that cloud must be conserved. As the cloud shrinks, the rotation accelerates. This process transforms barely detectable spin into violent rotation that shapes cosmic structure. The mathematics governing this amplification follows directly from angular momentum conservation. When gravitational collapse reduces the distance by half, the velocity must double to maintain constant angular momentum. Shrink the distance by a factor of 1,000, and the rotation speed increases 1,000-fold. Confirmed observations show this amplification in action throughout star-forming regions. Giant molecular clouds measuring hundreds of light-years across rotate so slowly that one complete rotation requires tens of millions of years. These clouds appear almost motionless when observed over human timescales, but sensitive measurements detect the rotation through Doppler shifts in the light emitted by gas molecules. One side of the cloud moves toward Earth, while the opposite side recedes at velocities measuring a few miles per second. When regions within these clouds begin collapsing to form stars, the rotation becomes impossible to ignore. A cloud fragment measuring 1 light-year across might complete one rotation every 1 million years. As gravity compresses this fragment down to stellar size, conservation of angular momentum demands dramatic acceleration. The distance to the rotation axis decreases by a factor of 10 million. The rotation velocity must increase by the same factor to conserve angular momentum. The collapsing cloud that took 1 million years per rotation becomes a star that spins once per month. This represents an acceleration of rotation rate by a factor exceeding 10 million. The star rotates 10 million times faster than the cloud from which it formed. Yet no external force added rotation to the system. Gravity simply concentrated the angular momentum that inflation created billions of years earlier. But gravitational collapse creates a problem that threatens to destroy star formation entirely. As the cloud shrinks, rotation speeds increase until centrifugal forces balance gravitational attraction. The cloud wants to continue collapsing, but rotation flings material outward with equal strength. The collapse stalls. The cloud reaches an equilibrium where it can shrink no further because rotation prevents additional compression. Scientists calculate that a typical collapsing cloud should stop contracting when it reaches a size measuring several astronomical units across. This distance equals the radius of Jupiter's orbit around our Sun. At this scale, rotation velocity increases until centrifugal acceleration exactly cancels gravitational pull. The cloud becomes a rapidly rotating disk that cannot collapse further. Stars should never form because rotation prevents the final compression needed to ignite nuclear fusion. Yet stars obviously do form. Our Sun exists. 400 billion stars populate our galaxy. Trillions of stars burn throughout the observable universe. Reality demonstrates that star formation succeeds despite the rotation barrier that physics predicts should prevent it. Something must remove angular momentum from collapsing clouds, or redistribute it in ways that permit continued compression. The solution involves magnetic fields threading through the collapsing gas. Charged particles within the clouds spiral around magnetic field lines while moving along them. These motions create friction that converts rotation energy into heat. More importantly, magnetic fields connect the collapsing cloud center to surrounding material at larger distances. Angular momentum transfers outward along magnetic field lines, while the central region continues collapsing. This magnetic braking allows the cloud core to shed angular momentum without violating conservation laws. The rotation does not disappear. It moves from the central collapsing region to the outer envelope, and eventually to the surrounding interstellar medium. The total angular momentum remains constant. but the distribution changes in ways that permit star formation to proceed. The same process operates during planet formation. A young star is surrounded by a rotating disk of gas and dust containing the angular momentum that could not be incorporated into the stellar core. This protoplanetary disk rotates rapidly because it inherited concentrated angular momentum from the original cloud collapse. Material within the disk orbits the star at velocities measuring tens of kilometers per second. Planets form through accretion of dust particles within this rotating disk. Small grains stick together through electrostatic forces and gentle collisions. These aggregates grow into kilometer-sized planetesimals that gravitationally attract additional material. Eventually, massive protoplanets emerge from the disk debris. Each planet inherits the orbital angular momentum of the disk material from which it formed. But planets also acquire spin angular momentum through countless collisions during the final stages of formation. When two planetesimals collide at an angle, the impact transfers angular momentum to both objects. Most collisions occur off-center, because perfectly head-on impacts are statistically rare. Each glancing blow adds rotation to the growing planet. Computer simulations following millions of collisions during planet formation show that random impacts naturally produce rotating planets. The final spin rate depends on the total angular momentum delivered by all impacts. Some planets receive more angular momentum and rotate rapidly. Others experience collisions that partially cancel their rotation and spin more slowly. But nearly every planet ends up with significant rotation, because random collisions almost never perfectly cancel angular momentum. Earth completes one rotation every 24 hours because billions of years ago, countless impacts during its formation delivered net angular momentum that gravity concentrated into the spin we observe today. That rotation originated as quantum uncertainty in a universe smaller than an atom. Inflation stretched it, gravity amplified it, collisions shaped it, and conservation laws preserved it across 4.5 billion years. But collisions do more than just create planetary spin. They also determine whether that rotation survives or gets redistributed across the solar system. When two rotating objects collide, their angular momenta combine through vector addition. This mathematical process determines whether rotation survives or cancels. Unlike random processes that create chaos, vector addition of angular momentum follows strict rules that preserve organized motion even during violent impacts. A planet rotating counterclockwise when viewed from above its north pole has angular momentum pointing upward along its rotation axis. A planet spinning clockwise has angular momentum pointing downward. When these objects collide, their angular momentum vectors add together like arrows placed tip to tail. If two identical objects rotating in opposite directions collide head-on, their angular momentum vectors point in opposite directions with equal magnitude. Vector addition produces zero net angular momentum. The collision cancels all rotation. This represents the only scenario where impacts can eliminate spin entirely. But this perfect cancellation requires extraordinarily specific conditions that almost never occur in nature. Real collisions happen at random angles with objects possessing different masses and rotation rates. These generic impacts produce vector sums that preserve most of the original angular momentum. A glancing collision between two planets transfers some rotation from one body to the other, but the total angular momentum of the system remains exactly constant. Conservation laws permit no other outcome. Confirmed observations of asteroid collisions demonstrate this principle. The asteroid belt contains millions of rocky fragments, ranging from grain-sized particles to objects measuring hundreds of kilometers across. These bodies constantly collide at velocities measuring several kilometers per second. Each impact redistributes angular momentum among the colliding fragments. Yet detailed surveys show that asteroids possess rotation rates consistent with billions of years of random collisions. Scientists analyzed the spin rates of thousands of asteroids and compared the distribution to computer simulations modeling random impacts over solar system history. The observed rotation rates match simulated predictions with remarkable precision. Collisions have redistributed angular momentum countless times, but they have not eliminated rotation. The asteroid belt continues spinning because vector addition preserves angular momentum even during catastrophic impacts. The same principle operates at galactic scales. Galaxies collide regularly throughout cosmic history. Our Milky Way will collide with Andromeda Galaxy in approximately 4 billion years. These galactic mergers involve hundreds of billions of stars passing through each other at velocities exceeding 1 million miles per hour. The gravitational chaos should randomize all motion and destroy organized rotation, but computer simulations of galaxy collisions show that rotation survives these cosmic catastrophes. When two spiral galaxies merge, their angular momentum vectors add together. If both galaxies rotate in roughly the same direction, the merged system retains strong rotation and may form a new spiral structure. If the galaxies rotate in opposite directions, the collision produces an elliptical galaxy with little net rotation, but the total angular momentum remains conserved. The Milky Way-Andromeda collision will create a merged galaxy that astronomers have already nicknamed Milkomeda. Simulations predict that this combined system will possess angular momentum equal to the vector sum of both input galaxies. The rotation will not disappear during the merger. It will be redistributed as stars settle into new orbits around the combined galactic center. Conservation laws guarantee that the spin present before collision must manifest in the final structure. Even more remarkably, collisions can actually organize rotation rather than destroying it. During planet formation, countless small objects collide and merge into larger bodies. Early collisions occur at random angles with no preferred direction. But as the largest objects grow through accretion, their gravity begins dominating the collision dynamics. Smaller bodies preferentially collide from directions determined by the gravitational field of the growing planet. This gravitational focusing creates a bias in collision geometry. Impacts from certain directions become more probable than impacts from other directions. Over millions of collisions, this bias produces net angular momentum, even though each individual impact transfers momentum randomly. The growing planet acquires rotation through the statistical accumulation of slightly biased collisions. Scientists modeling this process discovered that gravitational focusing naturally produces rotating planets from initially non-rotating debris fields. The mechanism requires no special initial conditions. Random collisions under gravitational influence automatically generate spin. This explains why nearly every planet in the solar system rotates. The collisions that built these worlds also spun them up through gravitationally biased angular momentum transfer. But collision dynamics also explain one of the most striking features of the solar system. All major planets orbit the Sun in the same direction. All major planets except Venus and Uranus rotate in the same direction. This coordination suggests that the planets formed from a single rotating disk, where collision dynamics preserved the original angular momentum direction. Random collisions in a non-rotating system would produce planets spinning in random directions. The observed coordination proves that planetary rotation inherited directionality from the protoplanetary disk. Venus rotates backward compared to other planets because a massive collision during its formation delivered angular momentum in the opposite direction. The impact was violent enough to reverse the planet's original spin. Uranus rotates on its side because a collision knocked its rotation axis by 90 degrees. These exceptions prove the rule. Planetary rotation persists unless catastrophic collisions deliver enough angular momentum to overcome the original spin. And even then, conservation laws ensure that the collision merely redirects rotation rather than eliminating it. The mathematics of vector addition explains why rotation dominates cosmic structure despite billions of years of violent collisions. Random impacts cannot cancel organized spin because vector addition rarely produces perfect cancellation. Most collisions redistribute angular momentum while preserving its magnitude. The rotation we observe throughout the universe survives not despite collisions, but because collision dynamics obey conservation laws that protect angular momentum from destruction. But this raises another question. If collisions preserve rotation, why do galaxies flatten into thin disks rather than remaining as spherical clouds of randomly orbiting stars? A newly forming galaxy begins as a roughly spherical cloud of gas with stars moving in every possible direction. Some stars orbit clockwise around the cloud center, others move counterclockwise. Some follow polar orbits passing over the galactic poles, others trace equatorial paths around the galactic center. This chaotic motion contains enormous kinetic energy distributed randomly across 3 dimensions. But over hundreds of millions of years, these spherical clouds flatten into thin rotating disks measuring 100,000 light-years across, yet only 1,000 light-years thick. The transformation from sphere to disk represents one of the most dramatic examples of self-organization in nature. Random motion becomes coordinated rotation. 3-dimensional chaos collapses into 2-dimensional order, and this transformation occurs naturally without external forces directing the process. The flattening mechanism relies on a simple principle. Collisions between gas clouds moving in different directions convert kinetic energy into heat while conserving angular momentum. When two gas clouds collide head-on, their motion cancels and their kinetic energy transforms into thermal energy that radiates away as light. The clouds lose energy, but their angular momentum must go somewhere. Conservation laws prohibit its destruction. Consider a gas cloud orbiting a galactic center at an angle to the average rotation plane. This cloud possesses both rotational motion around the galactic center and vertical motion carrying it above and below the midplane. The rotational component contributes to the galaxy's total angular momentum. The vertical component does not contribute to rotation. It represents wasted energy that moves the cloud away from optimal orbits. When this tilted orbit carries the cloud through the galactic midplane, it collides with other gas clouds concentrated near that plane. The collision removes the vertical component of motion by converting it to heat, but the rotational component parallel to the midplane survives because it does not oppose the motion of other clouds. After many such collisions, the cloud settles into a circular orbit within the galactic plane with all its vertical motion removed. This process operates on every gas cloud in the forming galaxy. Orbits that oppose the average rotation direction experience more frequent and more violent collisions. These collisions remove energy faster from retrograde orbits than from prograde orbits aligned with the majority rotation. Over time, the retrograde orbits disappear as collisions convert their kinetic energy to heat and radiation. Only prograde orbits aligned with the net angular momentum survive. Confirmed observations show this flattening in action within nearby galaxies. Young irregular galaxies contain gas clouds moving in many different directions. Their stars show no organized rotation pattern. But older spiral galaxies display highly organized disk structure, where nearly all stars orbit in the same direction within a thin plane. The transformation from chaos to order occurs over timescales measuring billions of years. Computer simulations following millions of individual gas clouds through galaxy formation confirm this collision-driven flattening. The simulations begin with spherical clouds of gas possessing random velocities. Researchers add only gravity and collision physics. No external forces guide the evolution. Yet after several billion simulated years, the spherical clouds naturally flatten into thin rotating disks, matching observed galaxy structures. The mathematics governing this process shows why rotation survives while random motion disappears. Angular momentum is a vector quantity that adds according to direction. Random velocities in 3 dimensions average to 0 when summed over many particles. But rotation around a common center accumulates because all particles moving in the same circular direction contribute positively to the net angular momentum. Collisions preferentially remove the velocity components that average to 0, while preserving the components that add coherently. After enough collisions, only the coherent rotation remains. The galaxy has extracted organized motion from chaos by using collisions to filter out everything except coordinated spin. This same flattening process operates in protoplanetary disks around young stars, the disk and dust collapsing toward the forming star. Random thermal motions send particles in every direction. But particles moving perpendicular to the rotation plane collide more frequently because they cross through the densest regions where most material concentrates. These collisions remove vertical motion while preserving rotation parallel to the disk plane. Over approximately 1 million years, the cloud flattens into a thin disk where all material orbits in the same direction. Planets forming from this disk inherit its coordinated rotation. This explains why all major planets in the solar system orbit in the same plane and the same direction. The protoplanetary disk filtered out all motion, except organized rotation before planets formed. The flattening process also concentrates matter into the galactic plane. Gas clouds settling toward the midplane increase the density of material in that region. Higher density produces more frequent collisions which accelerate the flattening process. This positive feedback creates the thin, dense disks we observe in mature spiral galaxies. But stars already formed before the galaxy flattened do not experience significant collisions. Individual stars almost never collide because the distances between them dwarf their physical sizes. A galaxy could contain 400 billion stars, yet those stars occupy only a tiny fraction of galactic volume. The space between stars remains essentially empty. Therefore, old stars formed early in galaxy history maintain their original random orbits. They do not settle into the galactic disk because they experience no collisions to remove their vertical motion. These ancient stars form a spherical halo surrounding the galactic disk. The halo represents fossil evidence of the galaxy's spherical youth preserved in stellar orbits that never flattened. Observations confirm this two-component structure in spiral galaxies. The disk contains young blue stars moving in organized circular orbits. The halo contains old red stars following random elliptical paths that carry them far above and below the galactic plane. The disk stars formed after flattening occurred. The halo stars formed before collisions imposed order on galactic rotation. This separation reveals the power of collision dynamics to organize cosmic structure. Given enough time and enough collisions, gravity and angular momentum conservation naturally create thin, rotating disks from spherical chaos. The beautiful spiral galaxies we observe represent the inevitable outcome of physics operating on rotating systems. The universe did not design these structures. They emerged automatically from conservation laws and collision dynamics. But if collisions create such perfect organization in galaxies, why do individual planets show such varied rotation rates and axis tilts? Planets inherit rotation from two distinct sources during formation. The first source is the rotating protoplanetary disk itself. Material orbiting within the disk already possesses angular momentum before it aggregates into planets. When dust grains stick together and grow into larger bodies, they carry the disk's rotation with them. This process naturally produces planets that spin in the same direction as their orbital motion around the star. The second source comes from countless collisions during the final stages of planet assembly. After planetesimals grow to sizes measuring hundreds of kilometers across, gravitational attraction becomes strong enough to accelerate collision velocities to several kilometers per second. These high-speed impacts transfer enormous angular momentum to the growing planets. Each collision either adds to or subtracts from the planet's existing rotation depending on impact geometry. Computer simulations tracking planet formation show that the final rotation rate depends critically on the last few giant impacts. A planet might experience thousands of small collisions that gradually build up rotation. Then, a single massive impact from a Mars-sized object can completely change the spin. This stochastic process means that planetary rotation rates vary randomly, even when planets form from the same disk under similar conditions. Earth's rapid rotation originates partly from a catastrophic collision approximately 4.5 billion years ago. A Mars-sized protoplanet called Theia struck Earth at an oblique angle. The impact vaporized both objects' outer layers and ejected debris into orbit that later coalesced into the Moon. But the collision also transferred enormous angular momentum to Earth. Computer simulations of this impact show that it could have given Earth most of its current rotation. Before the Theia impact, Earth likely rotated much more slowly, with a day lasting perhaps 14 hours. The collision accelerated Earth's spin to the point where one rotation required only 5 hours. Over billions of years, tidal forces from the Moon gradually slowed Earth's rotation to its current 24-hour period. But the rapid spin we experience today traces back to that single violent collision in the solar system's youth. Venus presents the most extreme example of collision effects on planetary rotation. Venus rotates backward compared to all other major planets. Its day lasts 243 Earth days, while its year measures only 225 Earth days. Venus rotates so slowly in the retrograde direction that its day exceeds its year. The sun rises in the west and sets in the east after moving across the sky for 117 Earth days. Scientists calculate that Venus originally rotated in the same direction as other planets, but a massive collision during the final stages of solar system formation struck Venus at precisely the right angle to reverse its spin. The impact delivered enough retrograde angular momentum to overcome Venus's original rotation and impose backward spin. No other explanation can account for Venus's anomalous rotation direction. Uranus demonstrates another collision consequence. The planet rotates on its side with its axis tilted 98 degrees from perpendicular to its orbital plane. This extreme tilt means that Uranus's poles point almost directly at the Sun during summer and winter. One pole experiences 42 years of continuous sunlight, while the other endures 42 years of darkness. Then the seasons reverse for another 42-year cycle. This bizarre axial tilt resulted from a collision with an Earth-sized object during Uranus's formation. The impact struck at an angle that knocked the planet's rotation axis sideways without significantly changing its rotation rate. Uranus still spins relatively rapidly, with one day lasting about 17 hours. but that rotation occurs around an axis lying nearly in the planet's orbital plane rather than perpendicular to it. Mercury exhibits yet another collision effect. The planet rotates exactly 3 times for every 2 orbits around the Sun. This 3-to-2 spin-orbit resonance is not coincidental. Tidal forces from the Sun coupled with Mercury's elliptical orbit naturally captured the planet into this specific rotation rate. But Mercury's relatively rapid rotation compared to Venus suggests that it avoided the massive retrograde collisions that affected its inner solar system neighbour. The gas giant planets Jupiter and Saturn rotate much faster than terrestrial worlds. Jupiter completes one rotation every 10 hours despite its enormous size. Saturn spins even faster, with a day lasting only 10.5 hours. These rapid rotation rates result from the planets forming through direct gravitational collapse of large portions of the protoplanetary disk. The disk material's angular momentum concentrated into the planets during their formation, producing the fast spins we observe today. But the rapid rotation of gas giants created its own problems. Jupiter and Saturn should have continued accreting disk material until they consumed everything within their gravitational reach. Their rotation should have increased continuously as more mass fell inward. Yet both planets stopped growing at masses much smaller than theoretical predictions suggested. Something prevented them from accreting additional material despite available gas in the surrounding disk. The solution involves the interaction between planetary rotation and the surrounding disk. Rapidly rotating planets create spiral density waves in the disk material through gravitational perturbations. These waves carry angular momentum outward from the planet into the outer disk regions. This angular momentum transfer removes spin from the planet while pushing disk material away. Eventually, the outward angular momentum flow balances the inward accretion rate. The planet stops growing because its rotation drives away the very material it needs to continue accreting. Observations of forming planets in distant protoplanetary disks confirm this process. Infrared telescopes detect gaps in disks around young stars where planets are currently forming. These gaps form because planetary rotation clears material from nearby orbital regions through angular momentum transfer. The gaps reveal that rotation actively shapes planet formation by determining how much mass planets can accumulate. The diverse rotation rates and axis tilts among solar system planets demonstrate that planetary spin depends on the chaotic collision history during formation. Unlike galactic rotation that emerges predictably from collision-driven flattening, planetary rotation remains sensitive to individual impact events. Each planet tells a unique story, written in its rotation rate and axis orientation. These rotational signatures preserve evidence of violent collisions that occurred billions of years ago. But planetary rotation faces another threat beyond collisions. Gravitational forces between planets and moons can gradually transfer angular momentum across the solar system, eventually locking rotation into configurations where spin appears to stop entirely. Earth's moon always shows the same face. Ancient craters visible from Earth have stared down at our planet for billions of years, while the lunar far side remains forever hidden from terrestrial observers. This synchronous rotation appears to violate the principle that angular momentum persists eternally. The moon seems to have stopped spinning relative to Earth, but rotation has not disappeared. It has been redistributed through a process called tidal locking. Tidal forces arise because gravity weakens with distance. The side of the moon facing Earth experiences stronger gravitational pull than the far side. This difference stretches the moon into a slightly elongated shape with its long axis pointing toward Earth. If the moon rotates faster or slower than its orbital period, the tidal bulge shifts away from the Earth-Moon line. Earth's gravity then pulls on the misaligned bulge, creating torque that changes the moon's rotation rate. Over millions of years, this tidal torque gradually adjusts the moon's rotation until it matches the orbital period exactly. Once synchronization occurs, the tidal bulge points permanently toward Earth. The moon rotates once per orbit, maintaining the same face toward our planet. The rotation has not stopped. It has been locked into precise synchronization with orbital motion through gravitational interaction. But angular momentum conservation demands that the moon's lost rotation must go somewhere. Physics prohibits its destruction. Confirmed measurements show that the missing angular momentum transferred to the moon's orbit around Earth. As tidal forces slowed the moon's rotation, they simultaneously pushed the moon into a higher orbit farther from Earth. The moon currently recedes from Earth at approximately 1.5 inches per year. This gradual separation continues today as tidal forces redistribute angular momentum from Earth's rotation into the lunar orbit. The Earth-Moon system demonstrates conservation laws in action. The Moon's rotation slowed from approximately 8 hours per day 4 billion years ago to its current synchronous period of 27 days. This represents an enormous decrease in rotation rate. But the total angular momentum of the Earth-Moon system remained constant. The rotation simply moved from the Moon's spin into orbital motion, carrying the Moon farther from Earth. Earth experiences the same tidal forces from the Moon acting in reverse. The Moon's gravity creates tidal bulges in Earth's oceans. As Earth rotates, these bulges drag slightly ahead of the Moon due to friction with the ocean floor and viscosity in Earth's interior. The Moon's gravity pulls backward on the leading bulge, creating torque that slows Earth's rotation. This process transfers angular momentum from Earth's spin to the Moon's orbit. Fossil evidence confirms that Earth rotated faster in the past. Ancient coral growth patterns show daily and yearly cycles that reveal the length of days when the corals lived. Corals from 400 million years ago indicate that Earth's day lasted approximately 22 hours. The planet has been slowing continuously as tidal forces transfer rotation into the Moon's orbit. In the distant future, Earth will become tidally locked to the Moon just as the Moon is now locked to Earth. When tidal locking completes, Earth will rotate once per month, keeping the same face toward the Moon permanently. One hemisphere of Earth will see the Moon hanging motionless in the sky. The opposite hemisphere will never see the Moon at all. This configuration represents minimum energy state for the Earth-Moon system. Once achieved, further angular momentum transfer will cease, because the tidal bulges will remain aligned with the Earth-Moon axis. But the Sun's tidal forces also act on Earth, complicating this picture. Solar tides will continue transferring angular momentum even after Earth locks to the Moon. The final equilibrium state remains uncertain. Computer simulations suggest that the Sun might eventually disrupt the Earth-Moon tidal lock by transferring enough angular momentum to change the orbital configuration. The ultimate fate of Earth's rotation depends on which tidal force dominates over billions of years. Mercury exhibits partial tidal locking with the Sun. The planet rotates 3 times for every 2 orbits, maintaining a 3-to-2 spin-orbit resonance. This configuration represents a stable state where solar tidal torques average to 0 over each orbit. Mercury's elliptical orbit creates varying tidal forces that prevented the planet from locking into 1-to-1 synchronous rotation. Instead, the 3-to-2 resonance emerged as the minimum energy configuration satisfying both tidal forces and orbital dynamics. Pluto and its largest moon Charon demonstrate the most extreme tidal locking in the solar system. Both bodies are mutually tidally locked. Pluto always shows the same face to Charon, while Charon always shows the same face to Pluto. The 2 objects orbit their common center of mass while maintaining permanent face-to-face orientation. This double tidal lock represents the final equilibrium state, where all rotational angular momentum has been transferred into orbital motion. The process that created this mutual lock required billions of years. Tidal forces gradually slowed Pluto's rotation from perhaps 10 hours per day to its current 6.4-day period, matching Charon's orbital period. Simultaneously, Charon's rotation slowed to match its orbit around Pluto. The system reached equilibrium where both rotation periods equal the orbital period. No further angular momentum transfer can occur because the tidal bulges on both bodies remain permanently aligned. Many moons throughout the solar system show tidal locking. Jupiter's 4 largest moons orbit synchronously. Saturn's major moons maintain the same face toward their planet. Even small irregular moons captured by giant planets eventually become tidally locked after enough time passes. The prevalence of tidal locking demonstrates that gravitational interactions naturally redistribute angular momentum toward minimum energy configurations. But tidal locking only redistributes rotation. It cannot destroy angular momentum. Every tidally locked moon still rotates. The rotation simply matches the orbital period, making it invisible to observers on the planet. The angular momentum that appears to vanish from the Moon's spin transferred to orbital motion, carrying the Moon farther from its planet or changing the planet's rotation rate. Conservation laws remain satisfied even though rotation seems to disappear. Tidal forces operate throughout the universe at every scale. Binary stars gradually synchronize their rotation with orbital periods through tidal interactions. Exoplanets orbiting close to their host stars become tidally locked within millions of years. Even galaxies undergoing collisions experience tidal forces that transfer angular momentum between merging systems. The universe constantly redistributes rotation through gravitational interactions, while preserving total angular momentum with mathematical precision. The Moon's synchronous rotation demonstrates that angular momentum can hide in orbital motion rather than visible spin. But conservation laws guarantee that the rotation never truly disappears. It merely transforms from one type of motion to another. This principle extends beyond individual planets and moons to the larger structures in the cosmos, where rotation patterns established at the universe's birth still govern motion across billions of light years. In 2014, astronomers analyzing data from the Sloan Digital Sky Survey discovered something that should not exist. Galaxies separated by hundreds of millions of light years showed correlated spin directions. Neighboring galaxies tended to rotate in the same orientation more often than random chance would predict. This coordination suggests that rotation patterns extend far beyond individual galactic structures into the cosmic web itself. Scientists mapped the spin axes of over 100,000 spiral galaxies and calculated statistical correlations between neighbors. The analysis revealed that galaxies within the same filament of the cosmic web preferentially align their rotation axes along the filament direction. This alignment extends across distances measuring 300 million light-years. Structures this large should show no coordinated motion because they exceed the scale where gravitational interactions can impose order. The discovery challenged understanding of how cosmic structure forms. Individual galaxies rotate because they inherited angular momentum from quantum fluctuations amplified by inflation. But the correlation between distant galaxies suggests that inflation created rotation patterns at scales far larger than galaxies. The cosmic web itself possesses rotational structure that emerged from the early universe and survived 13.8 billion years of cosmic evolution. Further observations confirm the correlation using different galaxy samples and independent analysis techniques. The effect remains subtle because only about 5% more galaxies align with filaments than random orientation would produce. But statistical analysis proves the correlation is real. The universe contains large-scale rotation patterns that connect galaxies across cosmic distances. Computer simulations of cosmic structure formation reproduce this alignment naturally. When dark matter collapses along filaments of the cosmic web, it creates tidal gravitational fields that preferentially torque galaxies forming within those filaments. These tidal forces align galactic angular momentum with the filament direction. The effect operates over hundreds of millions of years as galaxies form and settle into their cosmic web positions. But the simulations also reveal something more profound. The cosmic web filaments themselves rotate. Dark matter streaming along filaments carries angular momentum inherited from quantum fluctuations in the early universe. This dark matter rotation creates the tidal fields that align galaxy spins. The visible rotation we observe in galaxies traces back to invisible rotation in the dark matter web that formed before stars existed. Observations of galaxy cluster rotation provide additional evidence for cosmic web spin. Multiple galaxy clusters show coherent rotation, where member galaxies orbit the cluster center in a preferred direction. These rotating clusters measure tens of millions of light-years across, yet display organized motion, suggesting they formed from rotating regions of the cosmic web. The rotation present during cluster formation persisted as the structure evolved over billions of years. The largest known rotating structure is a galactic filament measuring approximately 400 million light-years in length. Galaxies along this cosmic thread show systematic velocity patterns, indicating rotation around the filament's long axis. The entire structure spins with a period measuring billions of years. This represents the largest coherent rotation yet discovered in the universe. The existence of cosmic web rotation means that the quantum fluctuations inflation stretched to cosmic scales contained not just density variations, but also velocity patterns that became organized rotation. These velocity patterns varied across space, creating regions where matter flowed in circular patterns around density concentrations. As the universe expanded and structure formed, these flow patterns became the rotation we observe in galaxies and galaxy clusters. Scientists calculate that the angular momentum in cosmic web rotation exceeds the combined spin of all galaxies by factors of 100 or more. Most cosmic rotation remains hidden in dark matter flows that produce no light and can be detected only through gravitational effects on visible matter. The galaxies we observe represent merely the tip of a cosmic rotation iceberg extending throughout the dark matter-dominated universe. This discovery fundamentally changes our understanding of cosmic structure. The universe is not just clumpy with matter concentrated in filaments and clusters, it is also rotating with organized motion spanning the largest observable scales. Every level of cosmic organization from planets to superclusters participates in rotation patterns that connect across space and time. The cosmic web rotation also explains why galaxies maintain their spin despite billions of years of potential disruption. Galaxies do not rotate in isolation. They move through a rotating cosmic web that continuously reinforces their angular momentum through gravitational interactions. A galaxy attempting to slow its rotation would experience torques from the surrounding web that restore the spin. The cosmic web acts as an angular momentum reservoir that stabilizes galactic rotation across cosmic time. Recent observations using gravitational lensing detected rotation in the cosmic web directly. Light from distant quasars passing through foreground dark matter filaments shows systematic distortions indicating that the dark matter rotates. The effect is subtle, requiring analysis of thousands of quasars to extract the signal from noise. But the detection confirms that dark matter filaments possess angular momentum that affects light propagation through the cosmic web. The rotation extends to the larger scales astronomers can currently observe. Superclusters measuring 500 million light-years across show coherent velocity patterns, suggesting rotation around their densest regions, these vast structures. Yet the motion exists and affects how galaxies within superclusters evolve over cosmic time. This cosmic choreography traces directly back to the quantum fluctuations that existed when the observable universe was smaller than a proton. Inflation stretched those fluctuations while preserving their angular momentum content. Gravity amplified the rotation as structure collapsed, and conservation laws protected the spin from destruction across. The universe rotates because it was born rotating, and physics provides no mechanism to stop the spin. But this raises a final question that strikes at the heart of cosmic origins. If rotation at every scale emerged from quantum fluctuations in the early universe, what set those fluctuations spinning in the first place? The answer reveals that rotation may be more fundamental to reality than the particles and forces that comprise visible matter.